So geology mysteries. Why are there so many mysteries in geology? Geology is known as one of the hardest scientists, not just because it's studying rocks, but also because there's a lot of tangible physical objects that can be objectively measured. Geology is a natural science which everyone has come in contact with and experienced in nature. Everyone's, gone to the beach and played in sand. Everyone's hiked a mountain and been able to see the rocks on the ground, been able to see the quartz crystals on the ground and lying everywhere when you're taking a hike. And so this is something that everyone's observed, everyone's been able to see in their life and been able to experience. And so this raises a lot of questions of why is it so hard for scientists today to really be able to... Why is it so hard for scientists today to really come up with all these theories and stuff? Because it's something so observable, something that's so simple and should be the most foundation part of science possible, and we don't understand it. So that's what we're going to be covering today. Alan Wade is going to be going into depth. I'm Spencer Wade. I'm just going to be giving an introduction to the universal model, and we'll go on from there. All right, so like I said, my name is Spencer Wade. I'm going to be doing an introduction. All right, so what is the UM? The UM is a book that is 27 years in the making, and it is a revolutionary book that changes the whole face of modern science. The purpose of the UM is to restore truth and order in science by identifying new natural laws. So what is a natural law? A natural law is a statement of truth. So in the universal model, we take this book, 100 scientists who shaped world history, and we kind of list them out in this little graph here. And basically what it has is it lists new observations, new technologies, and new theories where we're able to see from the past, from 500 BC to today, we're able to see what laws were made, what observations and what technologies and theories were made, all in this book. And so here we see theories, and up until the 1800s, there's no theories being made. There are no theories being made, and over here, we see a lot of laws, we see technologies and observations. And so we're able to kind of see, and it's kind of perplexing because today we're kind of used to, scientists coming out with theories, but right here we don't see any. But right here, about 1800, we see a lot of theories, and around 1850, we don't see any theories, or we don't see any laws being made, any new laws being made. No scientific laws that are being made. So we call this the scientific dark age. So as you can see right here, the scientific dark age is when there are no new laws being made, and there are a lot of new theories being made, so a lot of unfinished products being made. So not a lot of new truth and a lot of new laws. So the two biggest theories that you guys probably know of is the theory of evolution and the theory of relativity by Charles Darwin and Albert Einstein. And so with these new theories, we see this modern science puzzle where there's a lot of holes. It's all kind of jammed into each other. They don't really match up. Where this is nature's puzzle, this is where we're trying to get at, but scientists today aren't even trying to do that because they're just trying to make all their theories fit into each other and trying to make their ideas fit, when really what we should do is be trying to look for truth in this nature's puzzle here. Neil deGrasse Tyson said, "The good thing about science is that it's true whether or not you believe in it." And here in the universal model, we don't believe in that. We believe that we should be able to use observation and be able to experiment and be able to know truth by ourselves. We shouldn't be able to take it for all these evolutionists and modern scientists just take their word for it and just accept it as fact. And so this presents a big crisis. You know, the big crisis is we're just being told of what's going on, and we just kind of believing it, when really what we should be doing is be looking for these observations ourselves. And that is why Alan Wade said, "The best thing about science is you can observe, experiment, and do true science to discover the truth for yourself, instead of believing what theoretical scientists tell you." So here at the UM, we believe that science should stand on observation and experimental evidence that you can test. So what have we all been taught since childhood is in the center of our Earth? Can anyone tell me? Magma. Magma and an iron core, just like it said right here. So we've all been taught this ever since we were in elementary school. We've been taught that magma is in the center of our Earth. We have an iron core, and we're able to, and all that heat is able to travel around in the mantle. So if this is true, we should be able to take this basalt rock, which is considered a lava rock, and we're going to be talking a lot about rocks today, so kind of keep that in mind. We should be able to take this lava rock and be able to melt it with this torch right here, and it should be able to melt and make into lava, right? So here we are. We're doing this experiment, and we're melting this basalt rock, okay? And
in the can there, in the
so here we have a basalt rock, and this is what happened to it. If you can pass that around, it's a little broken, but so we have the basalt rock, and that black part is the part that we flamed it with the torch, and it didn't turn into lava. That's what we found out. It actually turned into glass. So in a way, that kind of doesn't make sense, because if it really is a lava rock, and if the rock cycle is true, then it should just turn it back into lava, but that's not what happened. So here at the UM, we actually say that there's actually a hydroplanet Earth model, where we have a rock water mantle, a liquid water outer core, and a solid ice inner core. And that's what we present as a true term and a true model that we're able to present, and that we can present with real evidence and real experiments. So here's one of the first experiment that's actually given in the book is the lava friction model. So the whole magma thing presents a question like, okay, well, so where does volcano come from? Well, what we present is that when we get tectonic plates and they're rubbing against each other with thousands of pounds of pressure, that it's kind of like when you rub your hands together, right? You go like this, and you're rubbing your hands, and it creates a lot of friction and a lot of heat, and you can tell that by your own experiment. And so with thousands of pounds of pressure with this tectonic plates, we're able to make that lava that's able, the rock is able to melt and able to produce those volcanoes that we talk about. All right, so this is one of the most revolutionary experiments of the book. It's called the hyprethermal quartz growth, where basically we're able to take a small quartz crystal like here, and then we're able to put it in the right conditions, which is high pressure, high heat, and in water. that we're able to double in size in one day. So we're able to grow in the right conditions rocks, which is a very revolutionary term. We hear all the time that, oh, rocks are made in millions of years, but we're able to double quartz crystal in one day. And that's one of the experiments that we're able to do in the book. So there wasn't a term in science so we had to create one, hypertherm. A hypertherm is a hyperthermal environment in which minerals can grow. So here we have hydro, pressure, and thermal, where we get hypertherm. So this is just a little diagram that we're able to see where we're able to have water pressure. We have our heat going on right here, and that is where we're able to see where the water is, or the rocks are being formed. So these are just this is just what the quartz growth experiment has revolutionized and what it's teaching us. Number one, it teaches how rocks are made. Number two, rapid growth in the right conditions. We're able to see that in the right conditions, we're able to double the size of quartz crystals in one day. New terminology. We have to make new terms. We know now that the pressure equals to make minerals is about 5.5 miles deep, which equals 13,395 pounds per square inch. Hyperthermal environment, geothermal evidence calls for marks of the flood. So a big thing that we produce in the book is that there has to be some type of universal flood because of there's no other place in the world that has this 5.5 miles deep of water that's able to make those minerals, and that's the only plausible experiment or explanation for the for making of rocks. We're able to see that sandstone, petrified wood, and fossils in dinosaur bones turned to stone about 4,363 years ago during the flood, and it didn't just happen millions and billions of years ago, like theoretical scientists tell you. It also changes geologic time and the age of the Earth, and it changes every single field of science. So the it contains hundreds of new scientific discoveries across many natural science fields, and it is the largest body of new scientific discovery ever published. So universal model obviously has some extraordinary discoveries and claims. That's what makes it such a revolutionary book. So in the volume 1, the Earth system, we're able to see, number 1, the Arizona meteor crater is not a meteorite impact crater. Most rocks do not come from a melt. Fossils can form in days, and it doesn't take millions of years. Most of the Earth's sediment is not from erosion. There is no magma inside of the Earth. The Earth is a hydroplanet with an ice core, and the largest rock formation on Earth is a salt pillar. In Volume 2, the living system, we're able to see that petrified wood and fossil shark teeth are not being formed anywhere on the Earth today. You can go in rivers, lakes, you can dig down, and you will never find a new shark tooth or new bones being made into fossils today, because there's nowhere on the Earth today that has that 5.5 miles deep of water that we're able to take a living organism and turn it into a rock and minerals. The oldest human tools are not the most primitive, and evolution is wrong. In Volume 3, the universe system, we see that most of the moon's craters are not from impact. E equals mc squared, probably the most extraordinary and probably one of the most well-known equations ever in science and math we disprove it. We say that it is wrong, and we explain why it is wrong. Na plus Cl does not make salt, and modern science's Earth density calculations are wrong. So modern scientists have not discovered any new natural laws because they are not even looking for them. Why are they not looking for them? The National Academy of Science said, theories are the endpoints of science. So why will the universal model be accepted by many without coming from a university or government institution? It's because truth is independent of its origin. So what is the UM? The UM is the largest collection of new scientific discovery that has ever been written. Mr. Wade, thank you for your time. Alan, will you please come up here and do yours?
Oh, I see. Thanks. There, I'll take that. Thank you. Yeah, good job. Thank you, Spencer. Excellent. So I'm going to be talking about the geology mysteries. And I hope you like this format where we have Spencer do kind of a little introduction, especially for the new people. I think that's good because if you haven't been exposed to the universal model, those are revolutionary ideas. So that's why we have to kind of review some of those basics that make it so different. And then today I'm focused on Chapter 6, which is the rock cycle pseudo-theory. And the universal model defines a pseudo-theory as a false theory that is taught as fact. And basically, it's full of a whole bunch of geological mysteries. And so that's what I'm going to focus on from the universal model today. And there's about 11 different mysteries. I won't try to read them all now, but we'll be going through them each as in turn. So the first one that we're talking about is the most abundant mineral mystery. And so I'm going to start with the question, what is the most abundant mineral on the entire surface of the earth? Yep. Okay, some of you already been exposed a little bit, because I don't think you could have said that before you learned about the universal model, right? You've learned a little bit already, so. And of course, having entire surface of the earth there, hopefully that helps give it away, because you got to consider the oceans as well as the land. Because on the crust of the earth, it would be more like quartz or feldspar, I think, is the most common. But if we're talking about the entire surface of the earth, we include the oceans, and so it is definitely included. So that's some stockpiles of salt from the Great Salt Lake. And where does modern science say that all the salt comes from? They say salt in the ocean comes from rocks on land. And so if the rocks on the land kind of got the salt washed out of them, we got to think about it close. And one of the things, I'll go ahead and pass around this piece of salt, and you can see, I mean, it's a pretty big chunk, but there's not like a lot of layers in it, not a lot of debris. And as we talk about this more, you'll see that would be telltale signs of if this was all from evaporation, like if it was being leached out of the land and washed out to the sea, and then the shallow seas were coming in and those were evaporating, then we would have shallow layers of salt, and then dust and debris and other things would get in, and then they'd go through that process again. So that's kind of what modern science says, that this happened over millions of years. But can all of the salt in the ocean come from the land? So we're going to kind of look at this salt mystery. If the salt in the sea could be removed and spread over the entire surface of the earth, it would form a layer that's more than 500 feet thick, above the height of a 40-story building. And so this is showing you San Francisco and covering up to about a 40-story level there. And you can see it's way up on the Golden Gate Bridge here in this picture. So that's a lot of salt, right? So think of that, 500 feet thick of salt covering the entire crust of the earth. Now the question is could that much salt erode from the land? Well, the continental crust rises on average, if we leveled out all of the continental crust, so it was all even, it would be 125 meters, which is 410 feet above sea level. So if we leveled out all of the continents, so we're taking all the mountains, right, and just smoothing everything out, we would have 410 feet of dirt or rocks, and they're saying that 500 feet, right? How could 500 feet of salt come from 410 feet of crust? Impossible, isn't it? So I guess we, yeah.
Does that account for how deep the crust goes?
Right.
How deep does it go below sea level?
I think it would go significantly deeper. So I'm pretty sure that the 410 feet is above sea level. But if it's getting washed out to the sea,
then what's below would be kind of still contain the salt.
would probably still contain the salt because it's got to get washed out. So I think that's why we're only focused on the 410 feet above sea level, because I don't see it washing from elsewhere. But yeah, that's a good question. So again, that's the salt mystery, and yet geologists say that the salt on the earth comes from the land, and understanding the mystery about the origin of salt is an important key to understanding the earth, because it is the most common mineral, or the most abundant mineral. And of course, last month we were talking about the magma pseudo-theory and was saying, well, modern science believes that the whole earth was a big ball of magma at one time, and so they believe that all rocks come from magma. But if you take igneous rocks, the rocks that are supposed to come from the magma, and you look at the elements, the materials that are in them, there's a lot of oxygen and silicon, and about 8% aluminum, 5% iron, calcium only 3%, sodium is 2%. So salt, we passed around that piece of salt, sodium chloride. It doesn't just come by putting those two things together, is what Spencer was saying in the earlier presentation. Salt, table salt is sodium and chloride together, but they don't just, you can't just mix the two and make salt. There has to be other things done to get the chlorine and the salt together. But what's more interesting here, not only is sodium a very low ingredient in the volcanic rocks of magma, but copper isn't even on the list here. And we're down, the last one there is lead at 0.002. So 0.002% is lead, and we haven't even got down to, whatever trace amount of chlorine there might be, right? So how is it possible that we take a great big ball of magma that would start to form igneous rock, and yet none of those igneous rocks have any chlorine in them? So again, where are we getting the salt from? Okay? No way to get salt. I don't even think we have enough sodium, let alone, and no chlorine. So we got a problem. And so that's the average composition of igneous rocks. So it really brings it into question. And it kind of ties in what we covered last month about the magma pseudo-theory with the rock cycle pseudo-theory, because they just don't fit. How is it that the most abundant mineral on the surface of the earth, salt, has no real origin in geology today? So it's a good question. What is the largest single mineral rock formation in the world? So here's another good question for you. I think you're whispering to each other. Go ahead and say it. Salt. It's salt again. Yes. It's Salt Dome. Yeah. It's out Avery Island, Salt Dome, in the Gulf of. Is it the Gulf of Mexico? Yeah, Gulf of Mexico. All right. Avery Island. All right. Perhaps there is one phase of geology in which we have accumulated more data, yet have more to learn about. It is salt dome geology. Ideas on the origin and mode of development have not progressed significantly from the stage of theory, despite widespread acceptance today of a few basic concepts. So we don't know a lot about it. And you can see this is going down 5,000, 10,000, all the way down to 35,000 or 40,000 feet. So deeper than Mount Everest is tall. And I don't think we even really know where the bottom of that might be. But okay, if the evaporate theory were true, thousands of layers of impurities would be evident as they would have accumulated in natural deposits. And this was another experiment where we took a quart of seawater, let the water all evaporate out, and we're left with just a very thin layer of salt. And so the modern theory, the modern science theory is that that salt came in as a shallow sea, evaporated, leaving this thin film of salt, and then another shallow sea would have come in, evaporated, leaving another thin film of salt. But again, if this is happening over millions of years, there'd be a lot of dust or other particles deposited there. Maybe even some plants would break through that salt layer and be growing there. And yet the salt that we find is nearly pure. I passed around regular salt before, and then this is Himalayan salt that has the kind of pinkish hue to it. And yet even though there's some impurities in the Himalayan salt, it's still like 95% pure. And other rock salt, like in the rock, in that dome, it's like 99% pure salt. And so we actually store our reserves of oil and gas down in holes that they've dug out of those salt pillars. And this salt is being deposited from California, and it has a little pinkish hue that actually comes from the microorganisms, the brine that organisms that live in that salty brine. And so that's why it has that pinkish hue. And again, we're not seeing that in the salt that deposits that we find in nature, except in areas like that where there is a lot of brine. Okay, salt is formed by methods other than evaporation, and so that's what we've got to think about. So that's the salt mystery. So let's go on to the real history of geology. Starts out with James Hutton. He is called the father of geology, And he came up with the idea that Earth was shaped by a long succession of reoccurring events. It's called the uniformitarianism here. And it's based on his ideas that we started out with magma, as we talked about last month, and then the magma gives us igneous rocks, like lava, and the rocks that are formed after a volcano erupts. And then those igneous rocks get worn away through wind and water erosion, and those sediments then are carried down to the ocean and laid down in layers, one after another, and so then we form sedimentary rock. And then those rocks, as more and more layers get pushed on top of them, then they get pushed down and there's more pressure on them, and the pressure then changes them into metamorphic rocks. So that's the theory of modern science, the rock cycle pseudo-theory, and we actually teach that to our kids in 3rd grade. So they just barely learned how to read, and we're teaching them this as if it's fact. And yet there's a lot of problems with it, a lot of holes in it. And so geology has actually become geotheoretical rather than geological. Because as you see in the mysteries that we talk about, there's a lot of areas where this doesn't work. So, you know, initially it sounds good as a theory, and certainly as a 3rd grader, they're not going to argue it. We all kind of accepted it, and we all learned it, you know, because it's nice because, you know, sedimentary rock, you can see the layers, and so people can look at that and say, oh, that's a sedimentary rock, right? But when you talk about metamorphic rock, I mean, even scientists can't tell the difference between a metamorphic rock and an igneous rock a lot of times. And so they're trying to figure out, because there's no real objective way to distinguish the two. One of the quotes I remember from the book said that it requires a lot of extra specialized knowledge that's not actually available. So, you know, you can't really decide. So, and so you look at these, right? I mean, this one you might think sedimentary rock, but most of those, you can tell they're definitely not sedimentary rock. Most of them are quartz-based crystals, but very unique, right, in their structure and origin. So anyway, we're going to look more at it. So we think, as I was saying last month, we said that magma pseudo-theory is a false theory that's taught as fact. There is no magma inside the center of the Earth. And we made those arguments last month. Of course, that's posted on YouTube if you missed it. But that's kind of the foundation of the whole rock cycle, because that's where everything in the rock starts. So if you take away magma, then the whole house of cards kind of crumbles. And here's a quote. Researchers expected when the new space probes checked out the rocks and minerals from Mars, they thought they would find water-related minerals like carbonates, clays, and salts, because looking at the surface, it looks like there's lots of areas of erosion and canyons, and so they thought that that in the past there would have been water that eroded those. But over the past 6 years, looked for and detected essentially none of those minerals. So we would agree that there's water erosion, but the environment is very different, because it's still not producing carbonates, clays, and salts. Okay? Yeah. That's kind of what we're going to get to. I guess for those who are watching on the video, he said, so those things require life. And I'm saying yes. So, and of course, we're going to learn a lot more about that as we go on in our chapters. This chapter is primarily the questions, the mysteries, what we don't understand. So, what celestial body in our solar system is this? Okay. This is actually a picture of the it's from a different side of the moon, so that's why you may not recognize it, because when we look at the moon, we always see the same side of the moon, and so it always looks exactly the same. This one is kind of taken from a little different angle than we see it, so that's why it may throw you off there at first. But it is the moon, and does modern science understand the moon and its origin? And we're going to find, no, they don't. Right. Basically, they think it formed when magma, a big meteorite came and struck the Earth and broke out part of it. And when it was melting the Earth, that big meteorite melted the Earth, it caused a piece of it to kind of ricochet back. And so you had a magma moon at that point, too. That's basically the theory. But it doesn't work very well either. The first footprint on the moon will probably be there a long, long time, maybe almost as long as the moon itself lasts, because there is no erosion by wind or water on the moon because it has no atmosphere. There is no volcanic activity to change the lunar surface features. Okay? So any things that would change that footprint aren't there. So it'll probably stay there. Okay, so let's go on to the sand mystery. So I'm going to go ahead and pass around this. Actually, I'm going to pass around both of these sands. This is kind of just regular sand, like from your playground. This is actually from the pink coral sand dunes in southern Utah. And yet you can see it's all pretty much exactly the same size and colors and stuff. And so we'll look at that more as we go. But you can be passing that around. Okay, the man has not yet lived who can adequately describe a grain of sand. I just thought that's a kind of a fun quote. So, sand is qualitatively defined as any particle that is light enough to be moved by wind, but too heavy to be suspended in the air. Okay? So if you have a strong enough wind, you can move it, but it's not just going to stay in air. Okay, if sand is the product of erosion, why are so many sand deposits homogeneous? In other words, they are all the same color and do not contain a mixture of all the minerals from the supposed parent mountain source. Okay, so these are sands from different places, and they may be different colors, but like the pink coral sand dunes that we're passing around here, you can see it's all the same pink color, or orangish, reddish color. Okay, and then this is looking at those same sands under a microscope. And what's I think is most interesting, some of these, like the Imperial dunes in California, you can see those are clear quartz crystals when you get them under a microscope and really focus on them. And then the pink coral sand dunes over here, the pink coral sand dunes, let me go back. As you look at those, you can see those are also clear quartz crystals when you're looking at them under a microscope, but they're very small, and they do have a little bit of coating of this reddish iron rusty color around them. So they've got coated with some of that orangish reddish sand, but or rust colors from the iron deposits, but basically it's clear quartz crystals. So anyway, that's very interesting. And those two on the right are also clear quartz. So we'll look at those a little later too. So here is the imperial sand dunes, and the enormous amount of magnetite, the iron ore sand, was collected from these sand dunes, and yet the mountains around them have almost no iron minerals. So how could if the sand eroded from the mountain, why is there a lot of magnetite in the sand but none in the mountains? And here's looking at it the other way. There's also a large amount of feldspar in the mountains around the imperial sand dunes, but that feldspar is almost non-existent in the sand dunes themselves. So looking at it both ways, it doesn't really match up. And so it doesn't make logical sense that the sand is coming from erosion. And on Daytona Beach, Florida, and Clearwater, Florida, the sand crystals, when we look at them under the microscope, they're very clear quartz sand crystals. And they don't even have the iron on them. So where is the clear crystal mountains, the clear quartz crystal mountain there, that eroded from? Have you ever been to Florida and seen that clear quartz mountain?
There's an extra special.
Something. So anyway, this mountain actually does not exist. This is a photoshopped quartz crystal mountain, okay? And I don't think there is any quartz crystal mountains on the earth. And so again, the sand on the beaches did not erode from the mountains. And so it had to be formed in some other way. You're suggesting some explosion. You know, we got to figure that out, right? Okay, so that's what we're going to try to do. Where did the red sandstone of Red Mountain come from? I mean, that's right here in Arizona. Red Mountain, very famous mountain with a characteristic shape. We just look north here and we see that. And yet, why are there boulders found within the sandstone? Why do you get a big, clear, or white, gray rock there? That's seen from a road cut right near Red Mountain. And you can see there's a lot of those gray rocks that were embedded in the sandstone. And yet, again, it just doesn't, the theories of modern science don't match up. It just doesn't work. And so that's why we have a sand mystery. And next we'll go into the quartz mystery. Now I'm going to go ahead and pass around this piece of quartz. Most people can recognize it because of the very unique shape of the point of the quartz. And even if you have a little pieces of quartz, the two that I'll pass around in these boxes, these are actually man-made pieces of quartz. And so you can, again, look for those characteristic points. And yet those are man-made quartz crystals. So we'll be looking at the quartz mystery here. Now, this, on the right, there is a dinosaur bone, and where the marrow used to be has been replaced with agate, which again is a quartz-based rock, but has some characteristic coloring to it, so it's called agate. And then over here, this nodule actually has a bone contained in it. So that bone inside of the rock, this is called a segmented nodule because it's cracked, and it looks like it's all broken in fragments or pieces. But it's all solid rock, and you can see close to the bone it's quartz crystals, that whitish color there. And so we've got quartz and dinosaur bones and these other nodules that have bone inside them. And it's making the scientists realize that these things form near the surface of the Earth. The plutonic textures have not been duplicated in the laboratory. However, the complete crystallization of the interstitial liquid as large crystals has not been achieved in granitic melts. Because going back to James Hutton and his theory, he thought that granite came from a melt. But they're not able to get the same textures. They're not able to duplicate that in the laboratory. And they're certainly not able to get large quartz crystals to form from a melt because they're a crystal structure, whereas a melt forms glass, right? Okay, and so here we have a geode, and these other, the other geodes there, all the pretty colors, some agate, those are from Brazil. And again, those are forming with a crystallization process, and crystals form from water. And we can't get those kinds of things to form from a melt. Now, surface chalcedony, I'll go ahead and pass around some of those. In fact, if you want to take a sample, I'll let everyone have a sample from here. Let's just go ahead and unscrew that, and everyone can take a piece of chalcedony. We call it surface chalcedony because it's found right on the ground. You can go out in the desert. There are several places in Arizona that you can go and collect these. That's what we did with these, is go collecting them out in the desert. And one side, the top side, has the crystal as shown up there on the top, and then the bottom or back side of it is dirty. And you may notice that on the piece that you take, there's one side that is prettier crystal, looks like a milky quartz, and the other back side may look rocky or dirty because that was sitting on the ground. Okay? And sometimes attached, like in the one in the bottom center there, that's a piece of rock that's about this big and has a nice big chalcedony crystal growing on it, or that grew on it. How can chalcedony be formed on the unconsolidated surface, just regular dirt, of the Earth and still be resting in its original position if it formed millions of years ago? Right? You may want to take your little piece of chalcedony that you're taking and go ask your geologist when that formed. And if they're telling you it's formed millions of years ago, how can I pick it up off the desert floor today and it not be washed, away or somewhere else, right? Why are they all face up, right? When they've gotten turned over during a million years? Some little animal kicking it over or something. Okay, here's back to quartz crystals. At the top, you can see the quartz crystals are forming on a rock. The bottom there is a rock of that top picture. And then we have broken fragments from Quartzsite, Arizona. And so it has the characteristic point on the top side, but the bottom side has been broken off. And so those are kind of obvious, and that's the way we usually see quartz crystals. But what I'm trying to show you here in this picture is these double-terminated quartz crystals that are, let's see, let me go ahead. I've got some of those as well, so let's go ahead. Can you go ahead and get the double-terminated ones out of there and pass those around? The double-terminated quartz crystals have points on both ends, which is really hard to explain in modern science because that means that they weren't growing off a rock the way we usually see them growing. They must have been growing by themselves, but how can they grow without a rock to grow off of? And the bottom photo there actually shows them with not only double terminated, but they're called twinned quartz crystals. So they have they're growing in two different directions and forming points on 4 different ends. Some of those. So again, lots of good mysteries. And the nice thing is we're going to be answering those questions of how those form later on in next month and the following month. Okay, the basalt mystery. Now, I'll go ahead and pass around some pieces of basalt. We'll start that over here on this side. Let's see, I guess that one's probably fine.
They say this comes from lava, right?
Right. They say that comes from magma. And that would definitely be an igneous rock, classified as an igneous rock.
I was curious to hold a rock from the Hawaiian.
Yeah. I do have some little bits of lava rock here, so I'll pass that around so you can see. And this picture is actually kind of showing, I'll come back to that in a sec. Let me get this quote in. No one has ever observed fine-grained basalt resulting from any continental volcanic activity. So we're not seeing basalt formed today. So one of the things you notice about that is pretty dense, pretty compact, pretty heavy, that little piece. And there's no holes in it like you see in what we traditionally think of as a lava rock. And some of those lava rocks actually have enough holes in that they'll actually float in water. But we're not seeing the fine-grained basalt forming. So let's look at this specifically. So the top one here is the basalt without vesicles, which is kind of what I passed around there as my example of basalt, because I'm trying to focus on the fine-grained basalt. And then the basalt with vesicles does have some of the holes in it. That basalt may not have as many holes as the little lava piece that I passed around, but it does have holes, which is indicative that there was some water that was turned to steam, right? That's how the lava rock forms when it's exposed to the air, and the cool air makes the hot water inside turn to steam and come out. Just like holes in your pancakes when you're cooking pancakes, right? Somebody related that. So that's a good analogy. Okay, so when was the last time you ever saw lava cool and form these types of columns? Okay, we got mountains of these big, huge, tall columns. So yeah, I mean, this is what we'd compare it to, right? Big columns. Are we going to see those forming in Hawaii? Right? Lots of lava, but I don't think we're going to see it looking like that. And here, notice these lava rocks have the holes and vesicles in them, but also notice they're all about the same size, which is kind of puzzling. And this is down near Yuma, big field of this. And where's the volcano? Where's the mountain that came from? So, again, a lot of puzzles and mysteries in the geology. So, yeah, where's the volcano that it came from? And then Devil's Tower here, again, has not only the tall columns, but they're in a hexagonal shape, a very characteristic shape of the basalt that is really unique, not only found here, but over in Giant's Causeway in Ireland, if you've ever heard of that. And it has those six-sided shaped and you can go bouncing around from segment to segment, walking on those like you're walking on the top of this. And here again we have the basalt again in columns. This is settled on top of the red clays. So we know of historic lava flows, but where is the basalt that's forming today? So if you get basalt from a lava flow, we should be seeing it forming today, and we don't. Okay, so the obsidian mystery. So we'll go ahead and pass around some obsidian as well. Obsidian forms when lava cools very quickly, according to modern science. And the elements in it freeze in a random order. The result is glass, which has no internal structure. Okay? So that's what modern science tells us. And it is a glassy kind of rock. You can kind of see through those pieces. And yeah, you can take a piece of that if you'd like. And you can see that it kind of breaks in a specific pattern, though, like when they're chipping away to make arrowheads. Okay, you can see a kind of a rainbow shape when it breaks. But notice on this mountain of obsidian, they're pretty much similar sizes, and yet jagged edges and stuff. So how do we get a whole mountain of this obsidian? And then Apache tears, if you round it, I used to collect these as a kid, and no one has ever observed a historical obsidian flow where these Apache tears are being formed. And so the question is, how do they really form? And this is obsidian on a mountain. This section down in the lower right, or lower left side here, is that dark obsidian, again, as part of a mountain. And how does that get there? Because it didn't come from a lava flow. And obsidian is another igneous rock. And so it should be coming from the lava. The iron mystery. I haven't. I should do that, but yeah. They actually do have a high content of water, so I would be worried that it might explode. I think it might be 30% water in those. So I'm going to have to try it. Try heating. He's asking questions about whether we've heated the obsidian and tried that experiment like we did with the other rock. That's a good question. We'll have to look at that. So what looks like the sparkling gold here in this stream is what's commonly known as fool's gold, which is iron pyrite. It is not as heavy as real gold, and it is more square-shaped iron sulfur sand that is usually always associated with the black iron sand as seen in this photo. But where does that iron sand come from? Whether it's the black filings that you've seen in streams, or whether it's pyrite. And here's a nice big large square piece, and this is actually in the rock where it was formed. So again, it's a pyrite cube, and this is coming from a mine in Spain, and so this is naturally how it forms. In fact, it couldn't be cut and polished to look that way. And so how is that forming, and why are the black magnetite and the fool's gold pyrite found in streams the same places? And then this one is a pyrite sun. How is this pyrite sun piece formed? These are found with coal deposits, and the coal miners would put them in their lunchbox and bring them out. Okay, so the cube, iron pyrite cubes, and so again, the desert, a stream in Wickenburg, Arizona, can see a variety of rocks and a large amount of black sand. How many of the rocks look black or appear to contain black iron minerals from which the iron sand could have eroded? The origin of this black iron sand is a mystery, and we can demonstrate that sand like this does not come from erosion by performing the iron sediment experiment, which is pictured next, where we take the sand from an area like that and we put a magnet through it and pick up a lot of iron filings, like on the left side there. And then on the right side, after we've crushed up the rocks on the bottom right, we crushed up the rocks from the same area, and we put the magnet through it again, but all we end up with is crushed rocks. We have no iron filings to put in our little jar there. So the rocks from where the iron filings came from don't contain iron. But the iron filings are right there in the stream beds. You've seen it in the stream beds before, I'm sure. And you've probably used a magnet and played with those iron filings. And then here, this is an interesting rock because it has those iron pyrite cubes, and it's in a rock that has quartz minerals and limestone, so they're all being formed together in the same place at the same time. And these things are found all over the world. We're finding beautiful rocks like this that have different minerals in, and yet how could they all form together? Okay, the ore mystery. Let me go ahead and pass around some of these samples of ore. Okay, the greenish on that would be copper ore that is oxidizing. This is the largest open pit mine deposit in the world, the Bingham Canyon Kennecott copper mine. It's located in Utah, and the ores have been called a freak of nature by some geologists. And that's because it doesn't fit in with the rock cycle pseudo-theory. They basically took this whole mountain and cut it all out. So this is before they dug it out, and that's after it's a huge canyon, the largest pit in the world. And there is no such thing as coincidence. We don't just comprehend the purpose yet and why these minerals are being found in these rocks and cracks and stuff. This one has some what looks like gold. I haven't actually have it tested, so I don't know if that's gold ore or if it's just iron pyrite in the rock. But anyway, there it is, some different ores and minerals down there. Those are good gold nuggets. If the earth was once molten, why didn't all the heavy metals sink deep into the earth? Because gold is very heavy and dense, and so, right, if the earth was a big ball of magma at one time, we wouldn't just have an iron core, we'd have all the gold and all the heavy metals.
Why wouldn't we have a gold core?
Down in the center. Right. Yeah. They have a gold core because it's heavier than iron. Good question. Why is it that certain specific ores are always found associated with other ores? And again, why are they near the surface? Where on the continents are ore bodies being formed today? Do we find ore being formed, right? Is there a new place where we're going to be able to dig a new mine? Okay. Now we go on to the carbonate mystery. And let me go ahead and pass around this rock that has a rather thick piece of carbonate on it, calcium carbonate. We kind of think of carbonate like hard water. Here in Arizona, we have hard water. And so after you shower and stuff, it gets stuck on the shower or around the tub. You get a ring of this carbonate deposits. And it's kind of this white, chalky formation. And according to modern science, there's 3 factors involved in making hard water. The amount of CO2 in the air, because carbonate is the CO3. So you got to have CO2 maybe to add another oxygen, and then you got CO3. And the amount of H2O falling through the air, like rain, and the availability of limestone source rock, which carbonic acid rainwater can dissolve. Okay? So sometimes it's referred to as a lime deposit, right? So calcium carbonate. So according to their theory, hard water comes from CO2 plus rain plus limestone source. Okay? But now we're going to look at a map and see, well, is it coming, do we have hard water where the rain is? So the red here is showing where the calcium carbonate is the highest and our hard water. So Arizona has a lot of red there because it has a lot of hard water. But you'll see on the map on the right where it shows average annual precipitation that we're not getting very much precipitation. Right? We all know we don't get much rain around here. We'd like a lot more rain. And so do these maps match up, right? Over there, we've got the green areas around the Mississippi River Valley. They get lots of rain. Okay? But they don't have much hard water, much calcium carbonate. So, yeah, it looks like the opposite, doesn't it? You're right. It does look like the opposite. So again, modern science theories don't seem to match up. Is there a biological process connected to the origin of carbonates? And you kind of asked that question earlier, and I think we'll be saying later that it does. But again, we're just focused on the mysteries today. So this is a flume where water's going through, and the flume in the hot sun, right, because it's up in this tin trough where the water, and you can see there's some leaking underneath there, and some of that calcium deposit getting deposited around on the underside. And like here is Fossil Creek, where we have lots of calcium carbonate being deposited, so much so that it's encasing the wood there in the center and a wire there on the right. And so it can form a pretty thick layer and fairly quickly under the right conditions. Why are there so few natural streams where limestone deposits are presently being formed? We gave that one example of Fossil Creek in Arizona, but it doesn't happen in a lot of streams, even in Arizona. And then we also have these kind of deposits in caves, like this is Kartchner Caverns, or Kartchner Caves, and it's showing you the cave entrance there. And the top of this cave is only about 4 to 5 feet thick. And yet modern science says, actually I think I have a quote for it here, it all began with a drop of water. A shallow inland sea covered this area 330 million years ago, deposited layers of sediment that eventually hardened into limestone, along with the other rock layers, and then it was uplifted from the Whetstone Mountains to form the Whetstone Mountains. So so you got to picture this, right? The top of that cave, only 4 or 5 feet thick on the top, and yet this was formed down under this shallow sea, and it was uplifted out of that without cracking or breaking. I mean, that'd be like an eggshell, right? So anyway, we don't think it formed that way. How can such a thin roof structure remain intact after hundreds of thousands of years of uplift and subduction and erosion? So there must be another process going on. Again, it's a mystery. The lowest mystery is another one. We have vertical lowest columns here. Okay? And you can see there's surface gravel on the top with your organic layers up there. But then all these columns, very thick deposits, some of these hundreds of feet thick, typically no horizontal stratification, like you would think of sedimentary rock. But it occurs in a single massive layer, 20, 30, or even more than 100 feet thick. And the lowest, so this is showing you some areas. Now, we couldn't find any map that shows where all the lowest deposits are. And so we actually, in the universal model, had to try to piece this together from what research we could find and what places we could find where they said that there was lowest deposits. It's probably much more than this, but this is the map that we made of worldwide lowest deposits. But again, they're very thick deposits. This is showing wind erosion, right? But these grains of lowest are like, it's almost like they're very fine grains, finer than most sands. Yeah. And water erosion, right? We're kind of familiar with wind and water erosion. But the particles with a diameter of 0.1 micrometers or less show no abrasion at all. So when we're actually doing tests with small particles, blowing it around, when they're that small, 0.1 micrometers, then we find they're not breaking apart anymore. And yet lowest is that kind of small. So if neither water nor wind rounded the fine particles which lowest is comprised, how did the lowest grains become rounded? And I actually saw 2 different pronunciations. Some called this lus, but I also found the pronunciation which says lowest, which looks to me more like what it is easier for me to look at and say lowest, but some say it's lus. So I don't know if that's based on different areas. Okay, and so when we really talk about the sand mysteries, we've got different sizes of sediments. So this is going from larger sediments all the way down to smaller and smaller sediments, and yet we have whole sections of sediment that's missing. So if it happened from erosion, you'd have a great big rock that breaks in half and then breaks smaller and breaks smaller, breaks smaller, right? Smaller, smaller, smaller. So we would have kind of an equal proportion of all different kinds of sand, all different sizes of sediment, if we kept breaking it down smaller and smaller. But this is showing you a chart of research where they have pebbles, small pebbles, and very small pebbles missing. And then we also have very fine sand and silt are missing. Very, very few in those sizes. And yet we still have the clays and the colloids that are even smaller, and yet that's so small that we can't break that apart through wind or water, because we've tried to, and it just doesn't happen. So the lowest mystery summary, no clearly defined origin of lowest in modern geology, no verifiable mechanism of how lowest was deposited exists, no comprehensive study of lowest has been performed, A complete worldwide map of Loess deposits has not been made, except for the one we tried to put together. Loess is a part of the untold story of sedimentology, and Loess is part of the missing sediment mystery because it's such fine particles. So we're going on to erosion here. This erosion, nobody recognizes that, do they? No. It's actually by Mount St. Helens. So a big canyon, right, because these are trees down in the bottom of the canyon. This canyon was carved out in a very short period of time after the eruption of Mount St. Helens, because you had a lot of material getting washed down through it. So there's at least 7 examples of the erosion mystery. I'm going to very quickly whiz through just a few of these. So the granite boulders, even like that round boulder there on the right, where's all the sediment around it? Where is it eroded? Where there's pieces? It's showing you real erosion in the middle, right, where you can see the pieces that have broken off and worn off through wind and water. And yet we don't have a pile of that under the round one on the right. Okay, this is Prescott granite erosion mystery. Again, on the right we have real erosion, but then where's the erosion around the other boulders over here on the left? Arch formations, right? Here's on the left, here we have one with falling rocks where the arch may be starting to form, but we've got these huge arches with almost no rocks underneath. And usually the rocks that have fallen out from underneath these arches, we can still see. So, because some of these arches have had some cave-ins where some of them have actually fallen down. But the rocks are very obvious. So how were these arches formed? And where's the erosion? Again, soil mystery here. We have unexpected thick layers. We would expect thin layers if it's getting, washed down from erosion. It'd be thin layer after thin layer after thin layer. But where do these great big thick layers come from? Where are the multiple missing layers of organic soil? Because after you have a thin layer laid down, then plants would start to grow. And then maybe you'd have water washed down and more sand deposited, and then another layer of organic material with plants and stuff. And yet, we only have one layer on the surface where we have organic material. And even all the layers of the Grand Canyon, they say formed over millions of years. There's all these layers, but where's the organic plants that would have grown in between each of those layers? How could all these layers of sediment have been laid down over millions of years and yet have no organic layers between them? And they packed their bags and left? Right, all the plants moved out. Okay, good. After each era. And the other thing is this was formed, modern science says this is formed in a shorter period of time than some of the spaces between the layers, which means that you would have time in between some of those layers to form a whole Grand Canyon. And yet, it's a flat layer with no erosion at all in there. Skipper rock mystery. Again, how are skipper rocks all made the same size and shape nearly, and usually always deposited in a layer of sand? Okay, so that's the erosion mystery. So how could they have eroded from the mountains and be deposited only in sand-sized sediments? Pedestal mysteries. How do these things form? Any ideas? And why are they still standing over millions of years? how did they become hardened in the first place, and why was the sediment surrounding them not hardened enough to stay there? Why was that all washed away and not those? Earth crust mystery. We've got a continental crust that on average is 36 kilometers thick on the continent, and it's called felsic because it's mostly made of feldspar or granite-like and is usually a lighter color. And then we have the oceanic crust, which is much thinner. It's only 6 kilometers thick, and it's called mafic because it is the darker colored rock like basalt or gabbro. Okay? And here's some of the granite. So I'll pass that around, right? So for comparison, right, here's the basalt rock that we passed around earlier. Again, the darker, dense basalt that is similar to the ocean crust, and yet the continental crust is a completely different kind of rock. And if they simply cooled from magma, you know, why is there such drastic differences in those crusts? So Pangaea is the idea that the supercontinent Pangaea broke apart into many continents we see today. Eventually, evidence was found that fossils and minerals from different continents match up, and so that's how they kind of piece this back together to make this puzzle. And later, seafloor spreading was observed, and the basis of the theory became more generally accepted. So this idea was originally rejected by scientists, but now it is an accepted scientific thing. The coal mystery is a part of this also, because coal is supposed to have come from peat, like peat moss. And this on the right is showing you where the peat grows, and on the left is showing you where the coal deposits are. And again, those maps don't quite match up, do they? Okay. So peat more up in the north and coal more in the south. So no correlation. Coal deposits are hundreds of feet thick, and peat deposits obviously are not, because it's just a plant, you know, moss. All right, so how do we get hundreds of feet of coal from peat? Okay, so that's showing you some of that layers of coal. Okay, so we've gone from geotheoretical to geological, or vice versa. And so this is the uniformity myth, is that idea of the rock cycle and how rocks are starting from magma and forming igneous rock, and then that getting worn away into sedimentary rock, and then that getting smushed really hard into metamorphic rock. And it doesn't really work. And so these are all the mysteries that we've gone through today. And if you have any questions you want to ask.
So do you go over erosion and what it really is?
Yeah.
Is that a mystery too in itself?
Well, just the idea that if the Earth is 4.5 billion years old, then, you know, there would be a lot more erosion than what we see. So, like, I mean, you look at the Great Plains, right? Huge areas that are all pretty much level, right? And there's some mountains in there sometimes, but we still have lots of areas that's just flat land for miles and miles and miles. And so where did that come from? And if it's millions and billions of years old, there'd be a lot more canyons or gullies or something cutting through that. And like this Saturday, I'm actually taking a tour up to the petrified forest too. And so we're going to be looking at some petrified rocks and stuff. This is a piece of petrified rock. And you notice it has very rough edges. And so it wasn't like worn away and smoothed down. If this formed millions of years ago, right, why isn't that all kind of worn down? And we'll be looking at the petrified logs up in the petrified forest, and we're not going to find a whole bunch of little pieces of worn down, wind, rain, eroded down around the bottom of those. So, yeah. Wood. You're saying living things like wood usually decay in a fairly short period of time. And so these were fossilized. How were they fossilized? How were they changed to stone? And so we're going to be looking at that, and that's kind of part of the erosion mystery, like you say. So yeah, next month we're going to be talking about the hydroplanet model, and we will be answering a lot of these questions. And yeah, today's the teaser. So hopefully you'll come back. And then the month after that, there'll be more answers too, and we'll be talking about the rocks when we go into the flood and how those rocks are made. So yeah. How come salt forms around oil? Oh yeah, you noticed on that big salt dome that there was oil next to it. And they have found that when they try to dig for oil, they know, if you got a salt pillar or something, that's a good place to go looking for oil. So again, that's a good mystery, good question. And we will actually be explaining that in the next month or two. I think that's will not be next month, but the month after that when we start talking about the flood. But yeah, and actually in my tour, we're not only going to the petrified forest, we're going to the painted desert, so I'll be explaining how that got colored and painted, and then to Meteor Crater, and Meteor Crater is actually on two fault lines. And so isn't it amazing that this meteor that came from outer space just happened to hit the target, dead on center bullseye, right where those two faults, earthquake faults. Yeah. So we're actually going to be explaining that it's a hydro fountain crater that exploded from inside the Earth where the weak spot, the fault line of two crisscrossing earthquakes were.
It wasn't a meteor.
So, yeah, we're... Really big bullet. Yeah. So anyway, we're going to be looking at the evidence of that too. So anyway, hope you come back or join us on one of our other events. You can find us on, good ending thought. Nature is too beautiful not to understand. And then Do True Science is my website and Facebook page, and the YouTube channel. So you can watch this and other presentations on Do True Science YouTube. And then Facebook is where I'm usually promoting the events and telling what's coming up. And then special thanks to Darren Clough for doing our video recording today. We really appreciate that. Let's give him a hand, huh? Okay. And you can find more at universalmodel.com. If you use the code DOTRUE, you can get a discount on the books, and we are selling some of the books and the summary book and the rock kits back there at the back table if you're interested. So thank you all for coming. Really appreciate it. And thank you all for watching at home. Thank you. All right. Appreciate it. That's it.